section 3.2, we're going to look at two important aspects of functions, the domain and the range. Mostly the domain, but we'll also look at a little bit about range. Domain is the set of inputs. And that's very often what we call the x values for a function, the things that we put into f of x, for example. The range is the set of outputs. And it varies from function to function, but we're going to look at some examples to see. Really, we're not going to look at the range too closely in this section. We're going to look at the domain. And for a quick example, by the way, these y values, those would also be f of x values. The function values that we get from different inputs, those are the output values. For this example, we're just going to look at a simple ordered pair function. So a function that's given by a list of ordered pairs. The first value of each one would be the x value, and the x value 1 corresponds to the y value 3. This x value 2 corresponds to the y value 4. The x value of 3 corresponds to the y value of 0. For us, though, what we're looking at in this example is the domain, or DOM for short, is the set of all the x values, or the input values, 1, 2, and 3. And that's it for that one. The range, or RAN for short, is the set of all the y values, which in this case, y values are 3, 4, and 0. I'm going to put 0 first, then 3, then 4. Just having the numbers in order helps to keep them organized. So this isn't the kind that we're going to be most interested in. This is a simple example, but x value, y value, all the x values of the domain, all the y values of the range. So what we're going to look at next is mostly domains. And a domain for a function, if it's not specified, is the largest set of real numbers for which the function is defined. So we're going to have the domain be as big a set of numbers as we can get away with. And we'll see that in some of these examples. First, by the way, we'll use the graph to talk about the range. It's easier to see and find the ranges of functions when we use the graph. But for these examples, we're going to find the domain of the function. And the first one I want to work with is f of x equals x cubed minus x plus 1. We'll study this type of function in a little more detail later, but for now, we're just trying to find the domain. We're not trying to graph or find function values. The domain is, in this case, any number I want, because I can take any real number and cube it, subtract the original number from that cube, and then add 1 to that result, and that gives me my f of x value for any real number. All real numbers. You can write it like that if you're not into the whole brevity thing. A quicker way to do it is to say the interval from negative infinity to positive infinity. That's the whole real number line in interval notation. And even quicker, you can use the double back R, or the double back capital R that represents all real numbers. Like I said, for the range, we would use the graph of this function, but in this case, it doesn't say to find the range, but the range is also all real numbers for this particular function. You would really have to graph it to see that. And just to give you an idea, this function looks like something like that. So it does keep going down this way, it keeps going up this way, keeps going to the right and left also. The domain is all the x values, the whole x-axis. And the range, it goes all the way up and all the way down, so the range is all real values also. Negative, positive, 0, everything in between. Let's look at a second example. So same instructions here. This time though, we're going to find the domain of f of x defined by the square root of x. So the square root function, pretty simple function. For any input value x, I take the square root, and that's my f of x value. That's my y value. Now for this though, for this expression to be defined, this expression is only defined for values of x that are greater than or equal to 0, or non-negative values. And so I need the x values that I put into the square root to be greater than or equal to 0, and then I can get a real number. Negative numbers don't work. If I try to take the square root of a negative number, I don't get a real number. So here I'm going to say that the domain is, it's all the real numbers that are greater than or equal to 0. That's, if you do it on a number line to get started, there's 0. I would shade to the right of 0 and use a bracket. But in interval notation, 0 to infinity, with a bracket for the 0, because the square root of 0 is well defined. It's just not the negative numbers. This next example, very similar. We'll find the domain of the function, the square root of x minus 5 plus 4. And notice that plus 4 is not in the square root. The only thing in the square root is the x minus 5. And that's what's going to determine our domain. To take the square root of something, that thing has to be non-negative, just like we saw in the last example. Only this time, that means x minus 5 has to be non-negative. X minus 5 has to be greater than or equal to 0. And if I add 5 to both sides, I get x is greater than or equal to 5. And that's what gives me my range for this function. In this case, the range is equal to greater than or equal to 5. So from 5 to infinity. And that's my, that is not the range. That's the domain that we're trying to find. Again, the range we would find from looking at the graph. Computing y values or computing function values, that can help to get started, but really the shape of the graph is going to help us decide which y values in the range. For this, though, we're just looking for the domain. Another example of this, still the same directions. In fact, this is the main thing we're doing in this section, is finding domains. I want to look at one more square root function and its corresponding domain. This will be our fourth one. F of x equals the square root of 7 minus x. Almost the same thing. What we need is for the 7 minus x to be greater than or equal to 0, so that we're not putting in a negative, we're putting in a non-negative number. And if I add x to both sides, 7 is greater than or equal to x. In other words, x is less than or equal to 7. So 7 greater than or equal to x, x less than or equal to 7 is just a more natural way of saying it. Either way, though, this is giving me the domain of all the real numbers that are less than or equal to 7. In other words, if I do 7 there on my number line, less than is to the left of, and less than or equal to means that I have the bracket. So it's all the real numbers from, well, all the way to the left, negative infinity, up to 7, including 7. And that's the domain. Another example like this is to look at the cube root. And the cube root has a different situation from the square root. The cube root has no problem with negative numbers. So if f of x is equal to the cube root of x, then I can put in any number I want. For example, the cube root of 1 is 1, because 1 cubed is 1. Here's another one. 2 cubed is 8. So the cube root of 8 is 2. That's another one that we can do pretty easily. But also, negative 2 cubed is negative 8. That's negative 2 times negative 2 times negative 2, a triple negative. That's negative. And so the cube root of negative 8 is negative 2. And this sort of thing is different from the square root. You can cube a negative and get a negative. Therefore, you can take the cube root of a negative, and the result is a negative. For this one, the domain is equal to all real numbers again. We can put any real number, positive, negative, or 0. Or you can write it faster like that. So that's the 5th example. Let's look at a couple more examples of finding domains, because there's another important type of function. This first one has been about radicals. We can't put a negative into a square root. So we can't, we have to restrict the domain of the function. For this one, it's kind of similar. F of x equals 1 over x. Now this one has no problems with negatives. The problem with this function is when I try to plug in 0. 1 divided by 0 is undefined. Specifically, it's not a real number. So I have to have the input value not equal to 0. It can be any positive number or any negative number, but not 0. And so in this case, the domain is all the real numbers except for 0. It would be negative infinity to positive infinity, except it's negative infinity up to 0. And we have to skip over 0 and go from 0 up to positive infinity. So that domain is all real numbers except for 0. And this is how it looks in interval notation. Finally, I want to go through one more example of this type of function. And that's with another one, a 7th example, which is f of x equals 5 over x plus 3. This is actually very, very similar to this one. What we have to look out for is we don't want a denominator of 0. So what would cause that to happen? X plus 3 equal to 0 would make a denominator of 0. I'm going to use an equation instead of try to do this not equals, not equals, not equals. Let's say x plus 3 equals 0. I'm going to find the bad number, or the restricted value, and here it's one step. Subtract 3 from both sides, x equals negative 3. Now that's the the bad number. That's the number that makes my denominator 0. You can see if I plug in a -3 in place of x, that's -3 plus 3 is 0. So that's the bad number. The domain is all real numbers except for -3, which I would write as -infinity up to -3, union with -3 up to infinity, which is the whole real number line except for -3. Now, to conclude our investigation of domains and range, we need to study range as we look at particular functions, but for domains and ranges, there's a machine function map picture. I'm going to call it the function machine picture. Function machine picture with an abstract shape here for the domain and another sort of shape for the range. And there's little x values that live in here. The domain is all the x values. I'm not going to use x for all of them. Let's call them A, B, and C. And then there's y values over here. Let's just call them W and U and Z to avoid the X, Y stuff for this. It's just inputs and outputs. And then the function is what takes these, the function f is what takes these inputs and puts them, assigns them to their specific outputs. So I just wanted to go over this picture a little bit. It's also called a map picture. We've got the inputs mapped to their specific outputs. Here I'm just doing it in a more general way. The set of inputs is mapped to the set of outputs by the function. We're going to look at another type of problem. That's another type of function in this section because of the domain issue. This is called a piecewise. So that word piece is what you should recognize from this definition. The piecewise defined function, or piecewise function, sometimes for short. We're going to just see a couple examples. First, the notation is to have the name of the function, f, of x, because the input is x, and equal to, I'm going to put a two-story brace because I have two different formulas. Now that wouldn't be a function. You're supposed to have one output, and this is two outputs. But in fact, we're going to make this one output by saying we'll use the first formula if the x is less than 0, and we're going to use the second formula if the x is greater than or equal to 0. And that's where the domain issue comes up. There's one domain for the function, but there's part of it for the first formula and part of the domain for the second formula. Let's evaluate this function for a few input values. I'm just going to pick some. We're going to find f of -3, f of -1, f of 0, f of 1, and finally f of 3, just to see a few values of the function. So f of -3, x is -3. That's not where I need to look, though. What I need to look is right here. -3 is less than 0, not greater than or equal to 0, less than 0. So I use this formula for -3. I put -3 plus 2 is -1. So I used the first formula because this number is less than 0, and I got -1. For f of -1, when x is -1, -1 is also less than 0. So I'm going to use this formula. -1 plus 2 is 1. For the third one here, f of 0, 0 is not less than 0. 0 is greater than or equal to 0. But fits this description, or this part of the domain. So I use this formula. 0 squared is 0. F of 1, again, 1 is greater than 0, or 1 is greater than or equal to 0. So this formula, 1 squared is 1. And finally, once again, 3 is greater than or equal to 0. So I'll use this formula, 3 squared is 9. And I have some function values. This is what you'll be doing to practice. I do want to show you what this would look like as a graph. Now, for this part, when x is less than 0, it's my x-axis. When x is less than 0, this is the line y equals x plus 2. So up here at 2, -1, -2, -3, for some x values. And my function is a line with an intercept here, only it doesn't really have the intercept there. I would leave an open circle because at x equals 0, I'm using this formula where we saw that f of 0 is 0. To the right here, 1, 2, 3, x greater than or equal to 0, I'll use this formula. That's a parabola. This is the curve y equals x squared, but I only use it for the right half. And this is the curve, it's really a line, but that's the y equals x plus 2. And it's only the left half of the function. So this piecewise function really, you can see why it has that name. Not only is the formula given in 2 pieces, but the graph is 2 different pieces. They're not always disconnected like this, but they're definitely 2 different shapes. I have one more example of a piecewise function that we're just going to evaluate, but it's going to show us something new about piecewise functions also. So for this example, I'm just going to have a formula f of x equals x squared if x is less than or equal to 1, 3 if 1 is less than x is less than or equal to 2. And that's kind of an awkward way to say it, but what I mean is x is between 1 and 2. Not including 1, but including 2. And then finally, the formula is x if x is greater than 2. And I got this function straight from the book example. So if you want to see a graph, they have the example, they have this example with the graph. I'm just going to use it to do the following values. F of -2, f of 0, f of 1, f of 2, and f of 4. So we're going to find these 5 function values that correspond to these 5 x values, these 5 input values, -2, 0, 1, 2, and 4. For -2, f of -2, -2 is less than 1, so I'm going to use this one. It doesn't fit here or here, it's this one. -2 is my x value, and -2 squared is 4. For x equals 0, 0 is also less than 1, less than or equal to 1. So I use this formula, 0 squared is 0. 1 is less than or equal to 1. It's not, 1 is not less than 1. It's less than or equal to 1, though. So again, I use this formula. 1 squared is 1. Finally, I'm going to get to use another formula. 2 is less than or equal to 2. In fact, 2 is between 1 and 2, if we're including 2 there. So this is the formula I wanted. If x is between 1 and 2, then f of x is 3. That's it. It's a constant function for that interval. And then finally, 4 is greater than 2, so I'm going to use this formula. F of 4, well, my x value is 4, and my f of x value is just x, whatever that value is, in this case 4. So f of 4 equals 4. So that's another example of what it means to evaluate a function. This time it's a piecewise defined function that's defined by 3 different formulas on 3 different intervals. Now, they don't really look like intervals here, but those 3 intervals are negative infinity to 1 bracket. That's what x is less than or equal to 1 means. 1 is less than x is less than or equal to 2. As an interval, that means 1, 2, with a parenthesis for the 1 and a bracket for the 2. And then finally, x greater than 2 means 2, infinity.